My name is Youssef. Yeah, so I'm a cryptographer at Consensus, working on GNOC, the ZK SNARK library, and Linear, the ZK EVM. And today, I'm going to talk about elliptic curves and SNARKs. So I have two problems in my life. One, getting my wife to choose a restaurant, difficult one. And two, Ethereum supports only BN254 precompiled. So today I'm going to talk about the second problem because the first one, we need more time, right? So what are these BN254 precompiled? So BN254 is an elliptic curve. So it is this mathematical object on which we can do some sort of cryptography. And mainly these three operations that we call precompiled, so they are like native smart contract in Ethereum. So you can do addition, like take 2 points and add them, have a third point. And you can do scalar multiplication, which is if you multiply a scalar by a point, so you get another point, which is like adding the points n times to itself, and the scalar. And pairing product check, where you have some bilinear map, it takes points on elliptic curves, output them on some line, some extension field, and multiplies these and check if it is one. So I'm not going to talk in details about these operations, but you can look at the illustrations and pretend you got it. So what is most important is what is it useful for. So it is useful for doing SNARK verification on Ethereum, doing BLS signature verification on Ethereum, like doing some polynomial commitment like KZG verification on Ethereum, and some Verkle trees, at least with what we have for now. And so we've talked about BN254 as an elliptic curve, but there are so many elliptic curves in the wild. And what I'm trying to explain today is why there isn't like a single silver bullet curve to rule them all. So you might have heard of BLS 12381, SECP256, so used for ECDSA signature on Ethereum. If you change a letter, you have another curve. You might have heard of ED25519, some 2 chains, some cycles like Pasta, Twiddle, some fancier names like Jub, Bandersnatch, Gramkin, and some new names like Lollipops. Yeah, so many names. So what I want to start with is some definitions of what is past, present, and future, right? So past are curves that have been used in SNARKs, but not anymore. Present, curves that are still being used in SNARKs today. And future is curves that already exist in the wild, but not used in SNARKs just yet. So if we follow this scalar scheme, then yeah. So we have some green ones in the past, like MNTs or Twiddle cycles, some blue, like BLS or 2 chains, and some future purple, like Lollipops. And yeah, we see that BN is half blue, half green. That is because it is still used in Ethereum, but it's not secure anymore, or at least it doesn't have the targeted security. So to organize this mess, I propose to categorize it into 3 columns. So I'm calling non-pairing friendly curves, pairing friendly curves, and in-circuit curves. So again, these precompiles, I talked about pairings, but not all the elliptic curves are equipped with pairings, or at least not efficiently. And if your SNARK doesn't need pairings, so you can use the curves in the first column. If your SNARK needs pairings, then you need curves on the second column. And in-circuit curves are this kind of curves that were built in purpose to do some computations over the SNARK. Not to do the SNARK, but just, I don't know, you want to prove some signature with a SNARK, then maybe building an efficient elliptic curve would help you. So if we take a closer look to the first column, so we have, for example, SNARKs like Bulletproofs or Halo or Nova. They can use the curves from the first column. But then the question is why there isn't like a single curve. Well, it depends on what you want. If you want performance, then maybe ED25519 is the best curve. If you want standard, maybe the next curve. If you're scared of NIST, maybe you choose another standard like Bitcoin or Ethereum curve, like SECP. If you want a recursion, that is, you want to do a proof of a proof, then maybe you can use SECU if you want compatibility with SECP. If you do not care about compatibility, you just want performance, then Twiddle. If you want more performance, then Pasta. If you want hybrid recursion, that is a SNARK from the first column and a SNARK in the second column, then maybe Pluto Aries or Gramkin, BN if you want compatibility with Ethereum. What about the second column? So the second column is for SNARKs that are pairing-based. Those are like GOT16 or anything that is based on KZG, like PLONK, for instance. So you can use any curve in the second column. And then again, why there isn't a single curve? If you want Ethereum compatibility, then BN. If you want performance, BLS12. If you want one recursion, that is a proof of a proof, maybe you want to use 2 chains. If you want infinite recursion with pairing base, so you have stuck with MNTs, but these are slow, either slow or unsecure. If you want some hybrid recursion, then you can also have other propositions here. So the last column is, so for example, if you want to prove some signatures like EDDSA or ECDSA or some specific hashes on elliptic curves or some vertical trees, then you can choose from this third column. But then again, if you want just elliptic curve cryptography, you might want to use job. If you want faster elliptic curve cryptography, maybe Bandersnatch. If you want pairing-based cryptography, then you need, for example, 2 chains or cycles, then BW6 or MNT, either you want one recursion or infinite recursion. If you want to mix things and make them succinctness, maybe the Lollipops. If you want to make them compatible with BN, then maybe Gramkin. So this is why we do not have like a single elliptic curve. But on Ethereum, we have a single elliptic curve. So what I want to talk about next is the story so far. So Goldwasser, Mikhaili, and Rakov, they invented zero-knowledge proofs, and there have been a lot of papers, both on the practical side and the theoretical side since. Yeah, a lot. But what I want to focus on is pairing-based SNARKs, because those constructions, they were based on different assumptions, and even those that were based on elliptic curves, we didn't care about which elliptic curves, because we can take any one. But starting with pairing-based, we started constructing elliptic curves in purpose for SNARKs. And for me, the turning point was this paper by Bonego and Nissim. It has nothing to do with SNARKs. It is a doubly homomorphic encryption scheme. That is, you can do any additions you want on the ciphertext and a single multiplication on the ciphertext, but it wasn't practical. And this is because for the decryption, we needed to solve a discrete logarithm problem. So not practical. But fortunately, so researchers like Gotz, Ostrovsky, and Sahai, between 2006 until 2000, until 2010, they built on top of this idea of doubly homomorphic encryption, because they said, well, it's not practical, but maybe in ZKPs we do not need to do decryption, we just need some sort of a commitment. Then maybe we can ditch decryption and we can have zero-knowledge proofs. And they did this. But we didn't have implementation at that point. And the turning point implementation-wise was this paper by Gennaro et al. They proposed insightful constructions for polynomial commitment, and mixing this with the pairing-based papers, pairing-based SNARKs papers, well, we started having implementation. And the first implementation I'm aware of is this paper called Pinocchio. And when I looked at the code, it was proprietary, still now. But they used a BN256 curve from another paper in 2010 by Nariga et al. And it had a 128-bit security at that time and 2 ADCT5. So the term was not coined to ADCT at that time, but it just means, for now, like, let's say, a performance metric. A few months later, there was this paper, Pawnee, where they implemented BST style license Pinocchio with another elliptic curve, BN254, from another paper in 2010. And it has a 2 ADCT 45 at that time, even if we didn't know about what is 2 ADCT is for. So same year, so Bensasson, Chiesa, and others, they implemented Pinocchio, a variant, and they used a very specific elliptic curve that I'm calling GMV6183. It is due to a paper to Galbraith, McKee, and Valença, and the implementation is still there today in libFF. It has a 2 ADCT 31. The 2 ADCT notion was introduced in this paper, but it had a security 80 bits. So so it is like, for those who know, it's just like an MNT curve, but with a cofactor equal to 4, so that they have like a twisted Edward form. So next year, pretty much the same authors, they proposed the famous BN254 curve, the curve that we are using today in Ethereum. And what they wanted is a 2 ADCT tool. I mean, BN curves were used in pairing-based cryptography, but in SNARKs, they wanted a 2 ADCT. So they constructed this curve with 2 ADCT 28. But my question is, why didn't you use the curve from Pantry? which has already a 45 to adicity, and both on the prime field, the base field, and the scalar field. And yeah, I mean, implementation-wise, the one that we have today in Ethereum is ugly, especially when you construct the tower, and this one was pretty much simple. But yeah, pairings were used in cryptography, and so the researchers have been working on the cryptanalysis of pairing, but the turning point cryptanalysis-wise was this paper by Kim and Barbulescu. So they found a new complexity for solving discrete logarithm problem over extension field. But to give proper credit, it was this paper in 2016, same year, by Meneses, Sarkar, and Singh, where they analyzed the conclusion, the impact of this Kim and Barbulescu paper on the choice of elliptic curves. And in their conclusion, they proposed using BLS12 curve. And for the record, BLS12, there were curves from 2001 and BN from 2005. And few people cared about BLS12 because of BN, but because of this paper, we came back to BLS12. And I believe based on that, folks at Zcash, especially Shenbo, they proposed the famous BLS12 381 that we're going to have now in Pectra upgrading Ethereum. Now, if you want like recursion, you need two curves. This is what we call two-cycle. So you need two curves because to express things efficiently in recursion, you need the curves to share some parameters. And it was this famous paper, Scalable Zero-Knowledge via Cycles of Elliptic Curves, by Ben Sasson et al., that proposed the first practical setting for recursion, and they devised the MNT 4289 and 298 and to MNT 6298. It has low security, big to adicity, and they also found another cycle, but they updated the paper only in 2020 on ePrint, 6 years later, I'm sorry. But they shared the code with, they shared the parameters with Coda folks, now Mina, and Mina used this at some point. So it is a paper from 2001, the construction of the elliptic curve, due to Miyagi, Nakabayashi, and Takano. But just to give proper credit again, so it was a paper of 2008 by Karabina and Teske, who established for the first time that MNT4 and MNT6 form a two-cycle. And yeah, so because of security, we need big parameters, and it was Orogevik who gave, I think, the biggest one so far of size 992. So it is not practical. I mean, it's slow, but yeah, for research, it's there. But the two-adicity is small, and it's very difficult to find a higher security with higher adicity MNT cycles. But I think 2 weeks ago, Costello and Korpal, they proposed this paper, Lollipops of pairing-friendly elliptic curves, and they solved the problem of higher to adicity for MNT cycles. And the idea was pretty much clever. They took the MNT cycles. I mean, the problem with MNT cycles is like you need to solve this generalized Pell equation, and to increase your search space, you need to increase the some discriminant, and the bigger the discriminant, the harder it is to find the curves. Let's put it like this. And what they did is like they took MNTs and they used some super singular elliptic curves with some other algorithm called Broker, and it works, but it is still slow, so not practical. And also Santos, Costello, and Naik, they looked at cycles of pairing-friendly, not elliptic curves, but curves in general. So, and they proposed some mix of elliptic curves, ordinary, super singular, and also some hyper-elliptic curves. So it is as slow as MNT, as far as I can tell, and also it is still early research. So implementation-wise, it's going to be difficult to do like this abelian varieties implementations efficiently. Now, if you want just recursion, but not infinite recursion, you just need to do a proof of a proof, maybe just for aggregation, you need two chains. So there is this famous paper called ZEXI. They introduced this curve called BLS2F377, which is used, I think, in Aleo and in Celo, others blockchains, and some Cox-Pinch 6 curve in, I think, 2020 on ePrint at least. And same year, we proposed another, so with the Orgilvig, another BW6 curve that was more efficient, and we generalized this to some other, to any elliptic curve and families, but it was just research. Implementation-wise, these two curves are like BLS12 and the BW6 are the most efficient nowadays for two chains. But it wasn't ZEXI that introduced the notion of two chains. It was 5 years ago, but hidden in some appendix of the paper Geppetto. So they used the same BN254 curve from Pinocchio, and they built on top of it a BW6 curve, giving the rise to the first implementation of two-chain. Yeah, but it was hidden in some appendix. Now, if you want to do a recursion without pairing-friendly SNARKs, you just need a recursion of some other SNARKs that do not need pairings, then you can use plain cycles. So in the Halo paper, they introduced the Tweedledum-Tweedledee 2-cycle, and then they replaced it with pasta, which is more efficient, and it is used now in Halo 2 implementation. It is used in folding schemes, like in the Sonobe implementation. But it was a year before that, at least I've seen a 2-cycle in the zero-knowledge setting. It was proposed in this website by Andrew Postra, and it is the SecP-SecQ curve, and in his mail he gave the parameters. So for me, it was the first one in the zero-knowledge setting. But research-wise, it was in 2011. It was called Amicable Pairs Under Adequate Cycles, and the Halo paper cites this one, actually. But actually, I was able to find an implementation of plain 2 cycles back to 2007 in a different context for primality testing. Like when you test primes, you can test them with elliptic curves. And it was François Morin in his implementation here, where he was discarding these plain cycles because they were bad for primality testing. And the same year, the definition was formalized in this paper by B. Mihailescu. It's called dual elliptic primes. So dual elliptic primes, amicable pairs, adequate cycles, and plain cycles, they are all the same thing. And I think 2 months ago, no, this summer, I mean this year, so Antoine Jou and others, they looked at elliptic curves that form cycle from a mathematical point of view, and they're calling it elliptic curves over hash pairs. So all of these the same thing. And if you want to mix then SNARK-based, pairing-based SNARKs and non-pairing-based SNARKs, you can use hybrid 2 cycles. So one of them is proposed by Daira Hoput from Zcash. So this is the one. And actually, I was able to find another implementation with BN381 in Mina protocol by Zach Meckler, but I don't think it was used anywhere. It was just experimental. And then if you want compatibility with Ethereum, so Aztec proposed the Gramkin curve that is compatible with BN254 from Ethereum. But actually, I mean, you can take any prime order pairing-friendly elliptic curves, and by definition, you can construct a hybrid cycle. And if you want to merge all of these, like you want to do a cycle and a 2-chain, so we're calling it lollipops, like you can have a cycle and then a stick. It can be pairing-friendly, it can be non-pairing-friendly, it depends on your use. But together with Antonio Sanso from EF, we proposed a way to build families of, like, when you have a pairing-friendly elliptic curve, and on top of it, you can have a plain cycle. And then, I think, a couple of days after our paper, Gilvik generalized our idea with some other families of curves like KSS. And then, I think, 1 week ago, on ePrint at least, Aurore and Simon Masson, they proposed an even more general way to construct those lollipops without with fixing the curve. Before we couldn't fix the curve, we had to construct all the curves together, but they were able to construct it on, for example, BLSO 381, for instance. And yeah, then lollipops, they found another way to do the lollipops with all the curves being pairing-friendly. It wasn't possible at this point, but they did it with super singular elliptic curves, which are defined over extensions, so make things a bit more slow. Yeah, that's it for me. So many information, but yeah, thank you.
Thank you very much. I'm here. Very nice. Good overview, covered a lot of stuff. There's a few questions, I think, too. One that kind of leads into the other, so maybe I can read out to you.
Yeah,
so, yeah, I think one that was asked even before the talk started, so I think you have a fan who's wondering, what is the future of curve-based SNARKs compared to hash-based SNARKs?
I was expecting this question, by the way. I mean, yeah, hash-based SNARKs, they are fast because you can construct them over smaller fields, so you can speed up things. But I still believe that curve-based SNARKs, they come with succinctness, so there is like a place for both. And today we see that, for example, for ZK-VMs or ZK-EVMs, they do a lot of Stark proving, so hash-based SNARKs, but then at the end of the day, they compose it or they wrap it with a curve-based SNARK so that they can get Ethereum compatibility one and they can get succinctness, which is like proofs are small. So I believe both are to stay.
Good. So do you think recursive SNARK into Stark might present an interest to be post-quantum? Here, SNARK cannot be simulated by post-quantum computer. How SNARK and Stark benchmarks?
Okay, so let me try to understand the question.
Yeah.
So I think, yes, SNARKs, if we're saying that SNARKs are based on curves, which is not really the case, but I understand it like this. Well, if it is based on curves, it's not post-quantum. Starks, well, if they are based on hashes, they are plausibly post-quantum. Composing both means that the protocol is not post-quantum. But yeah, if you want post-quantum resistance, then definitely anything that is hash-based. I mean, yeah, we can also talk about isogenies, because these are like curves-based. These are post-quantum, but I'm not aware of any isogeny-based SNARKs yet.
And so I think then the last part of the question, how do they sort of benchmark against each other in terms of efficiency? So, yeah.
Yeah, so it depends really on what's baseline we're benchmarking against. So it really depends, but for example, if we are taking any, so SNARKs, they work over like big fields defined by the elliptic curve. So if we define the statements over this field natively, then it's competitive. But in STARKs, you can define them over any field. And for example, if you define them over binary field like Binius, then you can do things like KZG faster. So it really depends on the baseline.
Nice, okay, good. Some more questions came in the meantime. We have 2 minutes left, so we can go into it.
Sure.
How important is high two-adicity, and can we get away without it?
Okay, yeah, so the two-adicity is, so in elliptic curves, we're working over this subgroup of prime order, and the two-adicity means just this order minus 1 has to be divisible by a high power of 2, and it just means FFT friendliness, because the best way to implement FFTs is like radix to FFT, and for big circuits, then you definitely need this two-adicity. For small circuits, maybe you can get away with smoothness, like just some smooth integers dividing like p minus 1. But yeah, for big circuit, like for example, I work on the linear ZK VM. We work on big circuits, so yeah, it's definitely a requirement for us.
And why do you want to get away without it?
I'm sorry, why?
I'm just asking my follow-on, like from my own understanding, why do you want to get away without it? Like, what problems does it introduce?
Yeah, so it introduces the fact that you need a specific elliptic curve. For example, if I'm talking about Ethereum, so Ethereum curve, so the R minus 1 is divisible by high power of 2, but the P minus 1 is not. So if you want to do, for example, a recursion over Ethereum, it wouldn't work on the second layer.
Yes, of course. Good. Then last question while we have 30 seconds left. Why is it crucial for recursion to have two curves where one is prime and the other, one prime is the order of the other?
Yes. So we express the statement of whatever we want to prove on the subgroup of the elliptic curve. And if we want to do a proof of a proof, we need to do the verification as a statement. But the verification uses these pairings, and pairings are defined over a different field. So if we want to do pairings in the subgroup, you need the field of the pairing to match the field of your subgroup so that computations are native. Otherwise, you need to emulate non-native field arithmetic, which is quite costly. I mean, we do this, but it's quite costly. But if you have native, then the number of constraints, so your proof generation will be way, way faster.
Good. I see there are more questions, but we're actually out of time. Maybe you can catch him offline. But yeah, thank you very much. I'm thrilled with the amount of questions. Great. Thank you very much.